The primary topic of section 10.6 is the ratio test. We'll also look at the root test in this section as well, but I even titled the section ratio test because it's by far the most important test of the section, and maybe the most important test that we'll look at of all of the tests. Usually whenever we're talking about importance of any type of test, ratio test is the top one, and then probably it's close between the limit comparison and comparison test as to the second one. Now, the ratio test, like I said, is probably the most useful convergence test. What the ratio test says is that if you have the general term of a series where the n is going to infinity, then if you can take the absolute value of the a sub n plus first term and divide it by the a sub nth term, and that's equal to some number L where that number L exists, then what we say is that that series a sub n converges absolutely if L is less than 1. Now, please think about what that means. If L is less than 1, then that means that the a sub n plus first term would have to be smaller than the a sub nth term. That's the only way that the limiting value would be less than 1. So that should make sense to you. If a series decreases, that should give evidence that it is going to converge, and then this is saying, well, if the limit as n approaches infinity of the a sub n plus first term divided by the a sub nth term, if that's a fraction less than 1, then this is going to be absolutely convergent. Okay, that makes sense. It's getting smaller, thus it absolutely converges. Now, we say it diverges if L is greater than 1. That should also make sense to you. The reason that should make sense is, how would L be greater than 1 in this scenario? The only way L would be greater than 1 is if the a sub n plus first term would be larger than the a sub nth term. And in that scenario, well, that just means that each term of your infinitely many term series is getting larger and larger and larger. Well, of course it's going to diverge in that scenario. Now, we say that the ratio test is inconclusive if this limiting value is 1. So what if you can't show that there's any size difference between the a sub n plus first term and the a sub nth term? We don't know. It could be convergent, it could be divergent. The ratio test is inconclusive in that case. But I would say most of the time it's going to diverge when L is 1, but we'll see that in some problems. But overall, the ratio test, it's only going to give an answer if L is less than 1, converges, L is greater than 1, diverges. Let's see that in action. So this first one, I have an alternating series, -1 to the n minus 1 power times n over 5 to the n, as n goes from 1 to infinity. Now, the alternating series test would work pretty well on this one, but I want to use the ratio test on this one. So I'll say, okay, the ratio test tells me to take the absolute value of the a sub n plus first term over the a sub nth term. So I go ahead, the first thing I do in all of my problems is I think about what that absolute value is going to be before I start trying to worry about the limit as n approaches infinity. If I just look at the a sub n plus first term, it's telling you wherever you see an n, put an n plus 1. So I have n plus 1 over 5 to the n plus 1. And then instead of dividing by a sub n, I just multiplied by the reciprocal of a sub n. So I said times 5 to the n over n here. Now you might wonder, what happened to my -1 to the n minus 1 power? Well, I don't need to worry about it, and think about why. Because it's an absolute value. No alternating sign is relevant anymore. So I just left that out of consideration altogether. So now we can say, well, this is going to become the group, and I gathered like terms in here, the two exponentials, 5 to the n over 5 to the n plus 1, and then the two polynomials, n plus 1 over n here. Now, 5 to the n over 5 to the n plus 1, that's easy. That's just going to reduce down to 1/5. Then my n plus 1 over n doesn't reduce nicely, so I just said this is going to be n plus 1 over 5 times n in the denominator. Now when I look at the limit as n approaches infinity of the absolute value of the n plus first term divided by the nth term, it gives me this, which I can then see, well, if n is going to infinity, the degree of your numerator and denominator is the same, so the limiting value is just going to be at the fraction of the leading coefficients, which is 1 over 5. Now, given my rule up here, anytime L is less than 1, so you'll see I have 1/5 is less than 1, therefore I know this series converges. Now I could even say converges absolutely. It's sufficient to say converges by the ratio test. Now for another one here, so this one converges because the limiting value is less than 1. Let's look at this one. We have the series of 3n plus 2 over 5n cubed plus 1, valid for n equals 0 to infinity. So I said, okay, the ratio test is only going to consider or concern itself with the absolute value of the a sub n plus first term over the a sub nth term. The a sub n plus first term, everywhere I see an n in this series, I need to replace it with an n plus 1. So I get 3 times n plus 1 plus 2 over 5 times the group n plus 1 cubed plus 1. Now I divide that by a sub n, or as I would prefer to do, multiply by the reciprocal of a sub n. So the denominator just went up to the numerator, numerator went to the denominator. And you might think, well, what happened to your absolute value? I intentionally didn't put it now because I know that everything has to be a positive power or a positive term of n or 0 anyway, so the absolute value is irrelevant in this problem. I just went ahead and dropped it. Now, simplifying this out, I know that my top numerator will be 3n plus 3 plus 2. That's where I got the 3n plus 5. I divided it by its like polynomial 3n plus 2 in that denominator. And then I multiplied by the terms of n cubed. This numerator is going to have 5n cubed plus 1, of course. Then I just brought this denominator over. I did not see any need to evaluate that group out, n plus 1 quantity cubed. And you'll see why in the next step. So now, my limiting value here, it's the limit as n approaches infinity of 3n plus 5 over 3n plus 2 times 5n cubed plus 1 over 5 times the group n plus 1 cubed plus 1. The place I'm getting that 1 times 1 here is because all I'm wanting you to remember, just like in the last problem, anytime you have a fraction going to infinity and the degree of the numerator and denominator is the same, you take the fraction of the leading coefficients. So you look at this first fraction, degree 1 over degree 1, this is being understood 3 over 3 as n goes to infinity, which is just a 1. Your denominator, this group is irrelevant because you're going to only have one leading term there, and it's going to be a 5n cubed in the denominator. Well, you have a 5n cubed in the numerator as well, so that's going to be, as n goes to infinity, this is just going to be 5 over 5, which is again a 1. So my limiting value is 1, which tells me, well, unfortunately in this scenario, the ratio test is inconclusive. No worries. We think about it more. So I went down here and I said, well, what about the limit comparison test? And I did the limit comparison test. I saw that the degree difference in the numerator and denominator was 2. So I compared it with the convergent series 1 over n squared. And remember, 1 over n squared converges because p is equal to 2. And anytime p is greater than 1, it's going to be a convergent p series. So I can say, okay, now, using the limit comparison test, I need to take the limit as n approaches infinity of the series I don't know something about's general term, which is right here, divide it by the general term of the series I do know something about, the 1 over n squared. And then I can say, well, this is just going to be the limit as n approaches infinity. If you're dividing by 1 over n squared, that's the same thing as multiplying this numerator by n squared. That's where this came from. 3n cubed plus 2n squared over 5n cubed plus 1. Then I see that that reduces down to 3/5. Now remember, in the limit comparison test, anytime the limit is equal to any finite number, that's evidence that whatever happens to this series happens to this series. Well, this is 3/5, which means as n approaches infinity, our series is essentially 3/5 the size of a series that converges. Thus, our series must also converge, and that's what I say here. Since the limiting value is 3/5, therefore we know the series of interest also converges. Now, it does not converge by the ratio test, it converges by the limit comparison test. Gorgeous problem. Okay, another one here. If I have the series as n goes from 1 to infinity of the geometric function 2 to the n divided by polynomial n down there. Well, in order to determine the convergence or divergence of this, I go through and I use the ratio test as I'm supposed to in this section. A sub n plus 1 becomes 2 to the n plus 1 divided by n plus 1. I'm multiplying that by the reciprocal of a sub n, which gives me the n over 2 to the n. Now I gather like terms. You'll notice I have the 2 to the n plus 1 divided by the 2 to the n times n over n plus 1. So now I can say, well, this first group, 2 to the n plus 1 divided by 2 to the n, that's just going to reduce down to 2. So I'll multiply that 2 by the n in the numerator, and I get 2n over n plus 1. Now, the ratio test tells us that we're supposed to take the limit as n approaches infinity of the absolute value of that a sub n plus 1 over a sub nth term. So I do that down here. But if I take this limit as n approaches infinity, the limiting value is 2. And notice, anytime the limiting value is greater than 1, you know that your test is going to diverge. That's what I said here. Since that limiting value is 2, therefore we know that the series of interest diverges by the ratio test. Gorgeous stuff. Now, you're thinking, well, this seems pretty straightforward. Well, students tend to have more trouble when I start bringing in problems with factorial. So let's make sure we look at some of those. If I give you the series from 1 to infinity over of 1 over the group 2n quantity factorial. So instead of just thinking about this, now just thinking about this in the beginning, I'm pretty darn sure it converges because that numerator is enormous and then that denominator is enormous and that numerator is tiny. So this should converge, and it should converge ridiculously quickly. But let's look at that. The a sub n plus first term over the a sub nth term, I can say, well, a sub n plus 1. All it is this group evaluated at n plus 1. So I have 1 over 2 times the group n plus 1, all quantity factorial. But then I'm dividing that by a sub n, so I multiply by the reciprocal of what I have here. I have the group 2n factorial in the numerator, and I really do need a parenthesis around that, otherwise it looks like n factorial times 2. So now I'll say, okay, my numerator is 2n quantity factorial. My denominator is 2n plus 2 factorial here. So I know that that denominator has 2 more terms in it than my numerator does. 2n plus 2 factorial would be 2n plus 2 times every integer less than that. So the next one less would be 2n plus 1. The next one would be 2n. But that one and every one thereafter would cancel with the numerator. So I just get 1 over 2n plus 2 times 2n plus 1. Now, when I start thinking about the limit as n approaches infinity of the absolute value of that a sub n plus first term over the a sub nth term, to where I get this, I can see that this clearly goes to 0. Now, is it a good thing for it to go to 0? Absolutely. You say anytime the L value is less than 1, it converges absolutely. So I can say, well, this one certainly converges. I have 1 divided by numbers going to infinity, so that goes to 0. Therefore, the original series converges by the ratio test. So then I can say, okay, that's pretty straightforward there. If I look at the next one here for number 5, it gives us the series, and this time it's a lot more complicated to think about. I give you n factorial quantity cubed divided by the group 3n factorial. So similar to what I had in the last problem in the denominator, this time the denominator is even larger. But that numerator, larger still, n factorial cubed. So this one we really need to analyze. A sub n plus 1 over a sub n, the absolute value is really not necessary because these are all positive values of n anyway. So you'll notice I don't even put the absolute value over here. And I just say, okay, the a sub n plus first term is going to be n plus 1 factorial cubed over 3 times the group n plus 1, all of that group factorial. We're multiplying by the reciprocal of a sub n, so the 3n group factorial goes in the numerator. the n factorial quantity cubed goes in the denominator. Now, when I went from this step to this step, here's what I thought. I know that this 3 times the group n plus 1 is going to be 3n plus 3 factorial. That's going to give me 3n plus 3 times 3n plus 2 times 3n plus 1 times the group 3n factorial. After that, all of it canceled with that numerator, but I still had these terms left in the denominator. This n plus 1 factorial to the third means n plus 1 factorial multiplied by itself 3 times. Each of those n plus 1 factorials is n plus 1 times n factorial. So I can say this right here, it means the same thing as n plus 1 cubed times n factorial cubed. Well, that n factorial cubed cancels with the denominator there. So then I can say, well, the remainder of that, the n plus 1 quantity cubed, I can just say, well, I'm going to have 3 of those in the numerator. Now, whether you show it as 3 in the numerator or whether you just show it as n plus 1 cubed, same thing. So down here, when I took the limiting value L, the limit as n approaches infinity of n plus 1 cubed over the 3 factors in my denominator, I can quickly see that the degree of n in the numerator and denominator is going to be the same. It's going to be n cubed. But the coefficient on n in the numerator is just a 1, whereas in the denominator you're going to have 3n times 3n times 3n for a 27n cubed. So now the limiting value of this is just going to be 1/27th, because you're just taking the fraction of the leading coefficients, since the degree of the numerator and denominator is the same. Anytime that limiting value is less than 1, there's evidence to show that that series converges by the ratio test. So we say our series, the summation of n factorial quantity cubed over the group 3n factorial, converges by the ratio test. On a side note, this is showing that the group 3n factorial is larger than n factorial cubed, which I think is kind of cool in and of itself. Now, that's the end of the ratio test problems examples for this section. Let me look at another test, not quite as important as the ratio test, but it could also be useful. It's called the root test. What the root test is stating is that if you can take L, where it's the limit as n approaches infinity, of the nth root of the absolute value of the a sub nth term, if that exists, then the series is going to converge absolutely. Now the decision choice is the same as the ratio test. It converges absolutely if L is strictly less than 1, diverges if L is strictly greater than 1. Just like the ratio test, the root test is inconclusive if the limiting value is 1. So now, looking at a couple of examples with the root test here, if I say, well, how about if I look at the series of 1 over 10 to the n? From the very beginning of this, I would think it converges because that numerator is small and that denominator gets large quickly. Should converge. Well, let's see. I do the nth root of the absolute value of the a sub nth term. Well, that's just the nth root of 1 over 10 to the n, and I know that if the nth root and the nth power just cancel each other out, it'd be 1 over 10 to the n over n power, which is just going to be 1/10. So you can say that cancels that out, gives you 1/10. Now I can say, since the limit as n approaches infinity of the nth root of the square root of the a sub nth term, didn't need an absolute value here, since that's just equal to 1/10 and 1/10 is less than 1, therefore my series converges by the root test. That one's pretty quick, pretty easy. Now, in some of these problems, I always prefer an indices of n, but some of them you'll see other indices in there. As you're working them, if you want to change whatever indices you're working with to n or to I, you're welcome to. In this problem, I have the index k. So the series from k equals 1 to infinity of -2 to the k over k to the 10th power. So when I'm thinking about whether this converges or diverges, I'll say, all right, I'll use the root test. And the root test, in terms of k is your number going to infinity this time, so I'll say I'll take the kth root instead of the nth root. It'll be the kth root of the absolute value of the general term a sub k. Well, that absolute value of a sub k, it's just going to allow me to ignore the negative alternating sign on that negative 2. So I say the absolute value of negative 2 to the k over k to the 10th inside the kth root. That's going to give me, in the numerator, the kth root of negative 2 to the k. The absolute value of that's just going to be the same thing as 2 to the k. What's the kth root of 2 to the k? It's just 2. Index divides into exponent. K over k leaves me an exponent of 1. But I do the same thing in the denominator. The index divides into the exponent of the denominator, and I get k to the 10 over k power. Now I can see it's okay to put this into my limit notation. I would say that the limit as k approaches infinity of my numerator 2 over k to the 10 over k power. Well, just think, as k goes to infinity, this denominator is going to be k to the 10 over infinity power. So that's going to give me k to the 0 power down there. So I can say, well, okay, now k to the 0 power, any number to the 0 power is 1. So then I can say, this is just going to be 2 over 1. And then the limiting value of 2 over 1 as k goes to infinity, it's just going to be 2, which is greater than 1. That's evidence that this series diverges by the root test. So I can say divergent by the root test because the limiting value was 2. Anytime the limiting value is greater than 1, that's evidence that it diverges. Okay guys, hope this helps you out with the ratio test and the root test. And again, please remember, by far the more important test in this section is that ratio test. So make sure you look at the problems dealing with that. That's a test that you're going to see used in future classes quite often.